Good afternoon, everybody. Thank you, Jürgen. So in the thin glass, it seems to be quite hype, and I'm happy for that because I'm working on it. And as my friend says, it's cool when the things that you like are actually hype. So I'm happy about it. And I'm going to talk to you starting from where thin glass actually started. So there's a video about where we all started to understand the potential of thin glass. So we can go on with the video. I will talk the way through. So thin glass started to be used mainly into mobile devices. And we all know it's very strong material, as the video is showing. And it has a flexibility and some properties which are really not common to what we are used to the glass at the moment. So here we see just a sort of an impact test made in the labs. And the weight applied, it will be shown shortly, and you will see how impressive this is, and also how thin this glass is. And yeah. So I always remember when I watched the Simpson movie, there was one of these scenes where there was this helicopter moving such a large shell. And if we have to imagine a shell coming, that can never be of normal glass. I like to think that this will be of thin glass. And so why we could do such a shell? Well, maybe clearly we cannot do this shell, but what are the properties? If we have to move it in that way, it has to be light, it has to be strong, and then it has to be flexible. So given this motivation, I will talk to you about what it is, thin glass. This is a question that has been bouncing. What do you mean when you talk about thin glass? How it is produced? Then some technical insight about the chemical tempering, in my opinion, a process which is quite fundamental for architectural application. And then I will introduce this Falcon glass, which is produced by AGC, and what thin glass testing I've been doing and what the state at the moment, and also comment a little bit on the test results, and then some conclusions and future work. So what is thin glass? Well, in the way we consider thin glass, we talk about a glass that goes from 0.5 millimeters to 2.1 millimeters. And here, just to give you an idea, visually, what 0.5 means compared to a 6 millimeter glass and all the other thicknesses. And if you ever had the chance to touch it, it's quite impressive, and it's very interesting. But what is the problem? Normally, up to now, most of the thin glass is produced either by the overflow process or the down draw process. And this leads that to be a sort of an expensive process. So in AGC, we started to say, OK, what can we do to make it cheaper? I will come back to this later. But now I want to switch into what is chemical tempering and why we need chemical tempering. Because clearly, being so thin, it means that the glass will break very easily. So chemical tempering essentially is also known as ion exchange. And so what you do, you put your glass into a bath of molten salt. This molten salt is with potassium nitrate. And at the temperature of 450 degrees, pretty much, the potassium nitrate, the potassium ions can exchange their position with the sodium ions in the glass. And these particles are they are much larger than the sodium. And so by taking a larger place, they create precompression. The problem of this precompression is that it cannot go very deep in the glass. And what does it mean? The precompression that I show in this picture actually includes a thermal tempering, which so is the normal, is the most common stress profile that we normally have in glass when we consider it temperate. And then there is the profile of chemically tempered glass. And as you can see, what we call the case depth or the depth of layer, which is the depth at which the precompression reaches the zero, is very narrow in chemical tempering and is much more robust for thermal tempering. And so if we take, for example, an image of a glass with an artificial scratch in this case, we see that these flows or these cracks tends to propagate quite deep in the glass thickness. That means that the depth of layer during the chemical tempering is quite important, and it's fundamental. And that's also another problem, is that thermal tempering will not be effective in glass thinner than 3 millimeters. So when we are talking about thin glass and we need to strengthen it, then chemical tempering is the protocol choice. And if we talk about increasing the depth of layer, an aluminosilicate glass does much better than soda-lime glass. Just to give you an idea in this graph, okay, so if you compare soda-lime glass with aluminosilicate glass in this graph, you can see the potential of case depth that you can build during a chemical tempering cycle against the surface compression that is generated during this cycle. And it's obvious here that with aluminosilicate glass, you can reach much higher depth of layer and much more significant compressive stress. But as I mentioned in the previous slide, aluminosilicate glass is normally produced by processes which are normally expensive. So where's the idea and where Falcon comes in place? We can think of a chemical composition of glass which is somewhere in between aluminosilicate glass and soda-lime glass, where we can build a case depth which is important for architectural application, and it will then work. And so that's where it all started. Why Falcon can be cheaper than normal aluminosilicate glass? Because it's produced by a float line. Why this makes it cheaper? Because for aluminosilicate glass or this sort of furnaces which are down draw or overflow melting, they reach very high temperatures, and therefore if you reach high temperatures, it means that your ceramic in the oven has to be more expensive, or it will have a lower service life. So the difference in price is not really on the material that you use, the base material that you use to produce it, but it's really in the method that you produce it with. And so we are capable to produce Falcon glass on a normal float line. And as mentioned before, the chemical composition is somewhere between soda-lime and aluminosilicate. And we think, and it was developed just to open new possibilities to the architectural world. And so where we are at the moment, I'm very excited because we don't have real project with customers that we are working at the moment, but it's more in a play environment, let's say. So, for example, we did in the lab this prototype of a triple glazing where we could compare a 4-3-4 glass. I mean that the two external pane are 4 millimeters and the internal pane is 3 millimeters. And we said, okay, what it will happen in terms of weight if we would change the glass composition there with all thin glass. This means that our outer panel goes to 2.1, the inner panel to 0.7, and the other external is 2.1. And I'm not sure it's very visible for you, so, but the balance there is showing that the 7.8 is the weight of my double glazing at the top, and 4 kilos is the weight of the double glazing at the bottom, which means that we have reduced the weight. Does that solve the problem? Not at all, because I said this is something we are doing in the lab, and I'm not sure whether from a deformation point of view, using 2.1 millimeter would be acceptable. But just to give you an idea that the weight gain here is significant. And also an interesting discussion is with the glass processor or glass installers is that, but how light do you want it to be? And one good target would be is that it can be manipulated by 2 persons. And the maximum weight for a worker would be 25 kilos. So this means that if we can make units that have a maximum weight of 50 kilos, then it can have an interest, because it means that the use of machinery is going to be limited, and possibly we can reach also some areas that can be more complex than normal. But this will vary from project to project, of course. Then other stuff, we try to bend it in some way and have something more about it later on. And if I read well here, we got 10 millimeters of span into this one. And so clearly there are testing going on. And this is another thing interesting with that we did, and which is bending with lamination. So you take 2 panels of 0.5 millimeters glass and you put it in the oven, you laminate it flat, and then you can heat up again your PVB, and it will keep the shape into the curved. There are lots of things to further understand into this subject, which has to do clearly with spring back effect, but clearly this is what we are doing at the moment. And then there is discussion, okay, when we are testing thin glass, is very thin. So if we do the standard methods, such as 4-point bending or coaxial double ring, what it will happen is that the deformation on your panel will be so high that really there will not be a correspondence between the theory and the practice. So some work in depth has started to see of what options we have to test this. And in a paper, I remember there was suggested to stick an aluminum plate on a piece of glass and therefore apply a pure tensile test. That's a very interesting insight. From my point of view, it would have been sort of difficult to have all these aluminum plates fabricated and so on. And on the other hand, we have a platform that we can use. It's essentially where I source my glass from. Even if I'm AGC, it's much easier for me to work with some sort of external startup that use AGC product. And I could create a sort of dog bone-shaped specimen. To describe you in more detail, this specimen here clearly is transparent. So essentially, there is here a space where I have a slot cut inside my glass. And then in this central part is where I want my glass to break, and this is the same slot at the top. So I'm doing a very simple tensile test. I was a bit scared in the beginning because I had some time constraints. So I said, OK, let's order this glass. Then if it doesn't work in the pure tensile test, we can still apply the aluminum plates and see how the testing is gone. It's tricky because clearly there are the edges of the glass and the edges on my slot where there could be some flaws which will trigger the fracture actually to occur. Oh, OK, this you can still see it, no problem. That will occur on the top. But luckily, out of 30 specimens, apparently it was well designed, 25 break from the center. I guess it's a good percentage if you even compare a normal 4-point bending where fractures sometimes even occur out of your loading span. And so this, for me, is a new way of testing. I'm testing chemically tempered, non-chemically tempered, and different edges conditions to see what's the real strength. Data are still in analysis for this sort of test. So as I'm talking, I know the technicians is doing tests on it. And then other stuff that we did is to see, indeed, whether this case depth of the glass that we have, it's interesting for architectural application. There was a study done by my former colleagues in the University of Cambridge, where they were aging the glass with some sand and some stones, and on normal soda-lime, I guess it was soda-lime, but chemically tempered glass. And as a result, after artificial aging and then doing coaxial double ring, the resistance of this glass dropped dramatically as to being comparable to that of annealed glass. So the question was, what happens with Falcon on this? And we did some tests, and I will show you results of this particular setup. And here, just to show you some more picture of the test. And also, another important property that people always ask me about is the fragmentation properties. So they say, because it's known that once you have very thin glass, the strain energy that the chemical tempering is introducing in the glass can be such that could trigger to some degrees of safe fragmentation. This picture shows you a panel after the test where you see a fairly coarse fragmentation, but I want to warn you, this coarse fragmentation is only there because there is the test load that was introduced. Normally, if I was impacting this glass with a spring-loaded punch, it will break just like annealed glass or even less than that. And what you can see is that as you break it with the load punch, the fragments doesn't even get to the edge because the residual compression is such that will tend to stop the propagation. So another point to take here is that thin glass, as strong as it can be for safety, we must laminate it anytime. But there are a lot of nice things that we can do with the lamination. So now let's go a little bit on the test results. You can see in these columns, SLSG stands for soda-lime-silica-glass, and FG stands for Falcon glass. And then I note down the processing. So I tested as reference non-chemically tempered glass. And then I have namely two types of chemical tempering, 460 degrees for 8 hours and 460 degrees for 24 hours. And then there's also the number of specimens for giving you an idea. And measuring the surface residual stress on that and the case depth, interesting things that will come as I comment on, and also some Weibull analysis for those who are familiar. If not, just have a look on the failure stress at a probability of failure of 1%. So let's start with some comparison. Let's compare Falcon glass with soda lime with the same chemical tempering. At a 1% probability of failure, we have 325 megapascal against 293. So these values are quite close, one with each other, possibly not enough to justify to produce a different type of glass for these sort of applications. However, things change if we start to analyze other things. For example, let's compare now Falcon glass as chemically tempered and with the sand abrasion. You see that the failure stress at a probability of failure 1% from 325 goes to 331. Considering a confidence interval, we are talking about the same value essentially. If instead we look on soda lime glass, we go from 293 to 59 megapascals. This, to some extent, confirms the work done by my colleague Corinna in Cambridge, but also tells us that the case depth is very crucial in this one. Indeed, if we go back to the column where case depth is shown, we got 48 microns for Falcon glass and 24 microns for soda lime with the same time of chemical tempering. So for me, these results means that the chemical tempering and values on the case depth and the surface residual stress are very crucial into this. And then another important remark is that if we consider a processing time of 24 hours, the case depth goes up to 79 microns, so it's even more important. But interestingly enough, and this is kind of already known in the literature, the surface residual stress decreases its value. What this means? That, honestly speaking, the resistance of this material is far more than we need. So it will be more interesting for us to have longer treatment with a larger case depth for some application. But what's also is important is that we can adjust the chemical tempering process according to the needs that we want. And I hope also that possible new standards that will come into this subject take into account that the case depth on the material is very crucial, so we cannot generalize the things. So to sum up, Falcon is a great candidate for thin glass of use in architecture, and because it maximizes the ion exchange due to the chemical tempering. It has a failure stress of 325 megapascals at a 1% probability of failure. We are talking about surface stress in this case. Edge stress will come really in the next weeks. And the Falcon failure stress did not decrease with aging. A longer treatment will benefit in terms of case depth, and we are really working into the development. I'm glad to have met someone who has done successfully some grinding on that. Currently, we work with laser cuttings, but I really see the need to implement also the grinding on the material. And it's very challenging from a process point of view. I hope I can give you this insight from a company where really handling a thin glass in a plant is not an easy task. And surely, if any of you has the chance to work with processors, they will tell you, and they might respond to you to some extent in a negative way. So if I go back to the Mike Pillois speech at the beginning, I hope that more and more glass processors, instead of telling you, no, we cannot do it, they will tell you, yes, but. And that's the yes, but that we are working at the moment, and we are doing quite nice things. And indeed, one of the nice things we are doing is this cylinder that you see there. It's a 0.5 millimeter glass, cold bent by hand by us in the lab, and it has 22 centimeters of diameter. It was very exciting doing in the lab. On the other hand, I expect it will break in the next few days, maybe during the next week, I don't know, because we are well beyond its possibilities. But that's why I said I'm happy in the way we are playing in the lab, because we are free to do a lot of funny things. Thank you for your attention, and I'm happy to take your questions.
Marco, thank you very much for this impressive presentation. We have a little time for a couple of questions from the audience. No question? Okay.
Good.
Question? Everything? Oh, there was one from Louis. Yeah.
What are your sizes available in terms of bird thickness, I would say?
In 2.1, we have the standard DLF and PLF size, so it's 3.21 times, I guess we arrive up to the jumbo size, so the 6 meters. As we go into smaller glass, if I'm right, the point size is stocked into 1.6 to 1.25 meters. But I'm going by heart. If you, to be more detailed, possibly the best way would be to the AGC website, where is the spreadsheet or the data sheet on this material, and that's specified. And to add up on your question, then there is a sort of startup within AGC, which is called Shape Your Glass, and they can deliver glass up to 80 by 80 centimeters, and that's because it's laser cut. So it really depends on how you want your glass to be done. In my case, I use glass for the labs, so it's coming from this Shape Your Glass thing and this laser cut. But if I need larger sizes, then I will have to hand cut it and find ways to grind it in a better way that is done currently.
And does AGC provides a chemically tempered one?
Yes, yeah. Yes. But we are not processor as big as the largest processor. That means on that we might have limitation. I don't think we have the jumbo size for chemical tempering. No. Yeah.
Thank you.
You're welcome.
Okay, thank you very much. Is there another question? Is not? Okay, thank you once again, Marco.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao!